All right, so we're recording, and the idea is that I will share my whiteboard and tell you a little bit about some ideas. So one thing that for sure I want to develop maybe in a few sessions is different ideas for convergence. The most important formula is something that I actually have slides for. This is a question of doing trotterization. So if I have a Hamiltonian H and I want and that Hamiltonian splits into two components. So one example is the transverse field Ising model, and then we have maybe X operations plus set operations. Okay, I will explain this notation also later, and at some point I think we will look at this kind of stuff. So this will be related to a question of Hamiltonian simulation. But I will also show compiling at some point, I think. And quantum compiling is a subject that usually is not covered in quantum lectures, so we will go more into that. But the most important question that almost everybody will at some point see in some quantum research or projects and so on, is that this is approximating e to I n times delta t HA plus HP. And now one thing that I will show in the upcoming videos and so on is what is the error. And today I will talk about how to even define an error. So today, very simple, motivate error measures. Okay, and that's actually a subject in itself a little bit. So what I wrote down here, this stuff here is called Trotter-Suzuki decomposition. And we can use it for something more advanced. So let's say we have a Schrödinger equation. So let me put maybe with a minus here, and the psi of t, and then h of t, psi of t. So I could consider some time-dependent Hamiltonian, and that time-dependent Hamiltonian could be a driven Ising model, for example. So again, same notation as before, but here I could have some lambda of t, I, z, I, and this lambda of t could be cosine omega t. Yeah, some omega. Right, so it would be driving the magnetic field up and down, and then the question is, how do you deal with that? So there are different notations that people use, and you will maybe frequently see some, I will put quotation marks for now because it might be confusing. Why is there an integral here? And then h of t. So this is called a time-dependent solution to the Schrödinger equation, and this is meant as a unitary operation ut, and then psi of t will be ut applied to psi, and psi of 0, and then I will put get notation just to make it clear. Okay, so this notation is actually pointless in the sense that it tells you more or less what will be happening. You will need some sort of time ordering, so I'm putting some t here, and a lot of operations that you need. And to me, this is more a placeholder of showing what's going on. If I come to Magnus expansions, there's something called Magnus expansion. And the point of those videos is also to maybe to give you some ideas and then get in touch and we can talk more. So not everything I can cover. I actually don't like Magnus expansions myself so much. So I won't be talking about them too much. I like them as kind of a piece of knowledge about quantum dynamics, but I don't use them myself too much. This is because it's an kind of analytic technique, but in the end, when I need something time dependent, I would do numerics. And that's kind of the point of those tutorials, that after a month or two, you will know how to set up your own numerics and kind of play with the dynamics of quantum systems in different ways and so on. So for example, I recommend looking up Magnus expansions if you particularly like this notation. Then actually the integral of dt h of t is meant as really an integral, and that would give you a time averaged maybe 1/t. That would be a time averaged Hamiltonian. And that's one. Objects like this actually play a role in the Magnus expansion, and then Magnus expansion actually gives you, in some cases, approximations to this full dynamics. Okay, so this is one notation, but I wanted to tell you more about Trotter-Suzuki decomposition, and the point is that actually we can use Trotter-Suzuki decomposition to define this unitary U that is actually driving our evolution here. The solution to this time-dependent Schrödinger equation defines a unitary operation, and now we will use basically maybe ut I can define as limits of n going to infinity, and then I can go with ei t divided by n h of t divided by n, and then ei t divided by n h 2 times t over n, then ei, I'm not defining too many things, but just to make it explicit, this would be delta t. And then at some point we will have I t still divided by this, but h of just simply t. So there will be n splittings like this. And now the point is, today I will kind of indicate how to discuss this. But for now, I'm just giving some overview for you to see some subjects. And this is not so obvious. So I don't know, think of in analysis, maybe the sequence of approximations to some Euler number or something like this. Getting like some convergence of a sequence is not so easy. But we can have two different things. We can ask ut is un t plus some error n t. So that would give us maybe a convergence rate, right? Because then we would maybe see that this is going towards 0 and this is going towards this. And the point is to think about what it really means to have those arrows here saying that this goes somewhere. And those approximations we will do with matrix norms, but I still want to highlight a couple of other applications of matrix norms before we can discuss things. So let's use the same notation now, psi of t, for again the Schrödinger equation. So here I wanted to say that this finding this gives something called the convergence rate. And convergence rate means how fast we get a good approximation. So when we will be doing some sort of operator analysis, we will be talking more about convergence rate, but this convergence rate is just a question of how to set up analysis and know how quickly the difference between our limit case and this convergence towards zero. So the difference is this operator here. So we need to know how quickly it becomes small, and then we need to know what it means for an operator to be small. And that's basically operator analysis, but we will do it in a simpler case where it's just basically linear algebra. So when I have something like this, there's a field in mathematics which studies when you have solutions to such equations. This is a linear equation, so the solution always exists. But in physics, there's something called the Dyson series. And in Petruccione or other textbooks, you will see people maybe sometimes having some time-dependent evolutions. So I was saying this maybe in quotation marks for this solution of the dynamics of a time-dependent operator. And then the Dyson series is actually something called the Picard-Lindelof series. And so this is more like quantum mechanics. And this is mathematics. But actually Dyson is quite open about it, that he always says that he took things from mathematics, and that's how he got his Nobel Prize for formalizing quantum electrodynamics and so on. But the piece of mathematics that he took is the Picard-Lindelof iteration or series. And the Dyson series looks like this. And this kind of explains to you why we are talking about integrals. So I will have the integral from, okay, maybe not T0 here. So I will have n integrals, and those will be nested integrals. So the last one will go until t, and then I have n minus 1 for dt n. And then I will have dt so it will be an n times nested integral tn minus 1 and minus 2. So this will look quite terrible, but that's fine. So now I'm putting here tn not minus 1. I'm putting here tn. Wait, now I'm confusing myself. But dt1 will go from t0 until t2. Then t2 will go until t3. So tn minus 1 will go from the previous one, tn minus 2, until tn. The next one, okay. No, all of them on the bottom are from t0. Sorry. So maybe if I will be showing this, I will be talking about simplices, and then it's clear why it goes from 0. Sorry, I didn't make some notes before. So we have an n-fold nested integral, and in the integrals I'm using capital N, so here I will also use capital N. And here we are actually integrating htn until ht1. Okay, so then it's this integral here is meant as sort of exponentiated integral, and integral exponentiated in the sense of, so additionally some time ordering here. This time ordering is implemented kind of by the order from tn until t1. And then if you sum it up, then it will give you this unitary operator. I still have to have I up to power n. My time dependence here, is kind of here, but okay. So this is not really to be trying to explain this in full detail, but you will see this Dyson series sometimes. And maybe later I will get some feedback to tell you more about the Dyson series, which is actually quite fun sometimes. But basically this tells us that there is a solution to this equation. And now if you look at this, this is more or less formalism. This is an infinite series, which is nasty. And if you look at my proposed solution here, using Trotter-Suzuki decomposition, is much nicer. Because with this, I don't know how to compute. This I don't even know how to put into a computer, but this I know how to put into a computer, okay? What I could do is fix n to be quite large, take those exponentials individually in NumPy, and then just go, okay? So that's my point here with different pictures about those time-dependent solutions. Okay, so I want to still tell you about matrix norms, and matrix norms will tell us about this convergence, will tell us about the convergence rate, and so on. And I also want to tell you about exponentials, because exponentials are actually the simplest case of using matrix norms. Okay, so let's consider a fiducial exponential of some matrix, and if A is an invertible matrix, or for example Hermitian, so let's say A is a dagger, so then we have that we can always find some diagonal matrix U, and then we just rotate here e to lambda 1 1, and then e to lambda n. Okay, 0 on the diagonal, u dagger here. Okay, so that's maybe the definition of an exponential. But for this kind of Dyson series stuff, I mean, the Dyson series looks nasty, but there's a different way of defining the exponential. You can go by definition, which would mean I go from n equals 0 until infinity, 1 n factorial, a to power n, okay? And if this operator is diagonalizable, we found a way of doing this. So that gives us some idea what's going on. But that will be the probably only thing that I will compute fully today. That will be something where we could say, okay, but this is an infinite series. So what does it mean to add infinitely many matrices? Okay, and as some refreshing example, for example, if I have 1 over n, and from 1 until infinity, then this is actually infinity. Okay, so if I'm just adding up infinitely many numbers, sometimes I get infinitely large numbers. Okay, and so if I'm adding matrices, we would like to know whether this is not a problem, and so on. And this will never be a problem, and the answer is Hilbert space. Okay, and the point why we are talking about Hilbert spaces, it's an axiom in some way. It's part of the quantum formalism to say the description of a quantum system is a state which is either a vector in a Hilbert space or is a normalized positive semi-definite functional on the Hilbert space. So one picture would be psi is in a Hilbert space H, or we could consider rho Hermitian and positive. I might talk more about those kind of positivity questions and trace rho is 1 and rho is a linear operator on the Hilbert space, right? So those are density matrices. So this maybe we could call a quantum state vector. This is a density matrix or quantum state. Okay, and the point of Hilbert spaces is that that you can ask when is a vector space a Hilbert space. Okay, so everybody can now check Wikipedia quickly and so on, but you will check and you will have one difficult thing and one property. There will be different properties to whatever. I don't remember how many properties you have. Because it has to be a vector space, it has to have a scalar product and so on. But the most important difficult property is every Cauchy sequence converges. So if you're like me, then you take some functional analysis book, you see the sentence, you throw it out, and then you come back to it 5 times and you still don't know what's going on. So I will tell you more about this. But now you see kind of where this is going, because what I'm trying to tell you is that I can have like very complicated operations. So for example, asking those kind of questions, if I split and keep splitting, will it converge or something like this? And I'm asking questions about compositions of unitary operators. So basically questions about kicking a system in different ways. And the physical operation of this kind of stuff is quantum control. So you have a quantum system, you have some parameters that you can change, and changing those parameters tells you how you change the dynamics in the system. So you can idealize this as kind of quickly kicking the system in different ways. Or you could say that I have a time-dependent evolution with some solution and some time-dependent Hamiltonian. That Hamiltonian might be smooth or not. And then I'm telling you the same question like in Hamiltonian simulation will also help you for time-dependent control of a quantum system. Okay, so that's why I'm talking about this, that's the physics. So for example, a qubit, if we control it with by applying voltages from outside, we are changing the frequencies of the qubit. So we are a little bit like changing this kind of lambda parameter here, but we kind of try to do it continuously. And in the end, in nature, everything will be continuous. It might be quite sharp, but it will be more or less continuous. So it will be a problem of this type. And that's when we control a qubit or a quantum processor, but by some voltages from outside, we will be changing those parameters. So we could call this outside control. And when I apply this classical voltage control to a quantum system, I can exercise quantum control. And what I will do is I will apply a unitary operator, which is in some way a composition of different operators in that way. So this is I started by talking about time-dependent Hamiltonians, and now I'm telling you about a huge field in quantum technologies, at least on the theoretical side, but it's kind of the only thing you can do to maneuver a quantum system is quantum control. Okay, and then I was telling you about a different way, this Dyson series and so on. And that will be also maybe useful down the line, but for now I just sketched it and I don't want to be explaining exactly those integrals, how they come about. But this is maybe a little bit obscure. And now the question, for example, that you could ask is that if I do this kind of summation of the Hamiltonians, integrate them painfully and so on, then apply them to my psi, but only n times, not infinitely many times, how well does it work and so on. So today I will show you some examples of how to get those questions. So now functional analysis comes into play because we start talking about, for example, this operation. And to even make sense of this infinite series, you need to understand the Hilbert space. And there will be 2 Hilbert spaces in question. So let me talk about, okay. So if I have psi, which is a complex vector c to power d, then we have the regular Euclidean scalar product, and it becomes a Hilbert space. It's this is actually relatively easy to understand. But now, for example, if I have unitaries and I have a sequence of unitaries, I would like to show that as n goes to infinity, I get a good limit u. And the way to do this in analysis is to say I have to have some measure. I have to have, I call it topology. And topology, if you have topology, it means you have a function that measures distances. So now we will do our distance measure for unitaries, okay? So one thing that we often do in quantum mechanics is, for example, to ask if I optimize over all states psi and look at the energy of the Hamiltonian, and then this will be our scalar product notation. Yeah? Then if I maximize over all states, I will get the maximum eigenvalue of the Hamiltonian. Okay. And actually for Hermitian matrix operators, this becomes actually a good definition of a matrix norm. So this is actually the operator norm of the Hamiltonian. So it has some sort of physical definition. And if we apply this to other operators, we have a definition of operator norms. So this is the kind of canonical operator norm. And now I want to motivate what it would mean to take a norm of what we believe would be a limit unitary and un. And for example, we would say that a sequence of unitaries un converges to u if the norm of the differences converges as n goes to infinity, converges to 0. That's kind of a natural definition, right? So if I would have regular vectors, so that could be n equals 1, that could be n equals 3, that could be n equals 4. And then I have more and more and more. And at some point they get here and all of them are here, right? So I would be looking at the Euclidean norm of the difference, and that would give me some difference. One point to make here is that operators form a vector space, and at some point I would maybe be explaining this as well. It's a different vector space than the CD, but operators on the state vector space are also a linear space. Okay, so that's maybe some exercises to discuss later. Normally in quantum mechanics, you don't discuss this in so much detail, but then in quantum info courses, maybe you actually discuss this, but there's usually never time. But when you don't do it carefully, you cannot study those kind of questions in detail because you're missing the language. So I'm just trying to develop a bit of this language here. So now I can talk about, for example, the sequence, let me call it En and sub A maybe. And I can talk about n equals 0 until n. So that would be partial sums of an exponential series, a to power n. And now I could ask, for example, exp of a minus summation n equals 0 n factorial an. So I could ask about this, and this would be some function of n. And if I can find this function, then that would give me a convergence rate. Okay. So I would have to find that function. But I want to do something else. I want to ask whether an operator valued series a to power n, whether that converges. So I would say it converges if this is less than infinity. Okay, and operator norms are also regular vector space norms, so they satisfy the triangle inequality. Okay. And here I don't need to explain much because it's just you apply a function to operators, you get numbers, and those functions which have this kind of double line notation, they just split in this way. Okay, so now I'm coming back and you will see that this 1/n example that I gave just before is not so trivial. So here I'm going further. Okay, and then operator norm is a to power n, and this kind of stuff you would need to read in Batia matrix analysis. Okay, and that's also not my point to be explaining all those details, because I'm not able to give a full lecture course on the linear algebra theory, but kind of pointing you there, and you can then discuss with me and so on and ask questions. So when I use this quick result from Batia, 1/n factorial, I get a to power n, okay? And this a, I can just call it a number a, which means that, okay, sorry, this was an inequality because I used this triangle inequality. N equals 0 to infinity, 1/n a to power n, and this is e to power a. And we know that this is strictly less than infinity, okay? So what I could do is I could correct this a little bit and put a capital N here. But then I can just put the inequality here, because taking n of those numbers, I can also add those non-negative numbers. So I can add it to the series, and this is just a regular series that we study also in analysis in physics and so on. So this is kind of easy stuff. So this is analysis of numbers. This is numbers. And here I have maybe operators. And now this infinity here doesn't make sense. Okay, so basically this partial sum is always bounded by e to power a. So if I take the limit, it will be always, its magnitude will be bounded by e to power a. Okay, and that's kind of the first step where you start using those operator norms. And what I used here is just two simple properties of the operator norm. So one property is just by definition, the operator norm has this. And most norms will have this submultiplicativity here. So it maybe will not be an equality but an inequality. Okay, so this is how we can start working with this. So
actually actually the like first thing you wrote, the series smaller than infinity, that doesn't like guarantee the convergence of the series, right? It can like alternate.
It can alternate still, yeah.
I mean, like after that, you show that like the last time also converges, so I guess it should be okay. But
yeah, so let me show. Yeah, thanks, Shungak. So I'm showing a weaker property, but I'm just saying that there could be many evil things that could happen, right? So I could construct a series, which is maybe 1/n and then a to power n, and then this will go to infinity for any a larger than 0. So I just wanted to show, okay, an operator series might diverge. It could be that this operator will become, you know, infinitely strongly changing the state or something like this. For unitary operators, that's not such a big problem, but yeah. So what I'm showing here is a necessary condition to have a meaningful convergence of a kind of sequence of operations. So first of all, it shouldn't diverge. But even if I know that it doesn't diverge, then the operator could be oscillating for forever and might never converge, which would be just some sort of cosine oscillation, right? So that's what Jongak says, okay? But I'm just trying to show kind of why it's non-trivial to be thinking about those convergence properties. For physics, the non-trivial part is to get those error bounds and convergence rates and so on. Okay. So I kind of motivated now the operator norm, just starting with the variational principle and trying to find the biggest energy, eigenenergy in the system. And that becomes our operator norm here. And now I said, okay, I could look at those kind of questions here. And for example, I already solved this problem, okay? So I solved this problem before it appeared. This is the exponential, okay? I mean, in the end, you will always do this. You will never sum up the series. But so we know that this exists. So this exists. Okay, and you can put a smiley face and be happy. Okay, I'm trying to overcomplicate things to show some ideas that come into play even for those simple cases. Okay, I mean, taking an exponential is one of the most fundamental operations in quantum mechanics, at least on the theory side. So that shouldn't be a problem, but then, you know, you encounter this series and there's something more to it. So for example, you could ask, it could possibly diverge, right? So the thing is that this has a polynomial dependence on the norm of A, and this is much faster than polynomial, and that's why it always is bounded. Okay, so that's what I showed here. So there's no problem here. Then I told you about this Hilbert space, and when is a vector space a Hilbert space, and there's this key property, every Cauchy sequence converges. So let me show you one case where I could look at this. So what does it mean that if our operator vector space is a Hilbert space, and it is a Hilbert space because it's a finite vector space, so it's fine. But using the fact that this is a finite vector space, then En and En plus 1A, this should go to 0. And this is this Cauchy property. Okay, so then we say that ENA, where N ranges in positive integers, is a Cauchy sequence. Okay, and my Hilbert space, so to speak, is linear operators over this Hilbert space. So it's a vector space and so on. But then this property coupled with this tells me that limit of ENA is again an operator. It is a well-defined matrix. That's all. So all this kind of Hilbert space stuff says that if you take the limit, it will be just a matrix. It will be a single matrix. You might not know exactly what this matrix is, but it exists. Okay. So it's actually an important property. Okay. Because now you think about, okay, so let me consider E, and now I will actually do this kind of notation, T1. EI delta T H of Tn. Okay, so I fixed delta T to be T over N. Okay, and then this defines for me UN and maybe T. Okay, and here this kind of convergence question is not so easy. So Jongrak stopped me and said, okay, you're showing that maybe it's I showed this necessary condition. So it's bounded, so it has a chance to converge. But now this one could oscillate, right? It could oscillate for a long time. So for example, here you would ask, okay, you would be checking UN T minus UN minus 1T, and whether this goes to 0. If this happens, it means you have a well-defined unitary. And one thing that we can show next week is that actually this kind of stuff happens. This is actually not so interesting for physics, because what is more interesting for physics is to show that this converges to a well-defined unitary, and then to get a bound on UN approximating this limit. So here get a function f of n, and this function f of n should be decaying, and then you go, okay? So that's basically nice, because let me now lead with that. So let's say I can do this kind of approximation unt minus ut is bounded by f of n. So then I could say, okay, so maybe in the lab I can apply pulses. And now the question is, how fast do I have to apply pulses to be changing the Hamiltonian to approximate this time-dependent Hamiltonian that I want to apply? Okay, that would be the physical question. So question, how fast kick control parameters? So sampling rate. Okay. And if I have this f of n, it might give me some number. So maybe f of 100 will give me 0.1. And then I say this is, or maybe 0.01. Okay, so it's a tiny number. It's much smaller than some imperfections in the system, then I'm happy. Which means I have to change my Hamiltonian 100 times, and I will have this kind of discrete sequence of changes in the Hamiltonian, but it will be essentially what I wanted in the first place, this continuously changing Hamiltonian. Okay, so that's one point here. Okay, so those matrix norms you can evaluate in NumPy. Exp of A you can also evaluate in NumPy. So you can evaluate the norms, you can evaluate this. So if you understand the mathematics of this, you can analyze different proposals for protocols. Okay. So my point with this is that I showed you like a little bit of a deeper dive into some questions that use language of functional analysis. But actually what they amount to is to tell you when is a theoretical proposal. So maybe I have a theoretical proposal. So there's a theoretical proposal. And this proposal says how to implement. And what you want to implement is a theoretical protocol. Okay, so this theoretical protocol could be a quantum algorithm. Or it could be a quantum gate. So it could be some primitive operations that then you use in a quantum algorithm and so on. So that theoretical proposal should use maybe some time-dependent pulses, which means the hardware Hamiltonian, the physical Hamiltonian of the qubits will be changing over time. And then you want to say, okay, I want to use this theoretical protocol that I just proposed, and I want to implement it. So I need a theoretical proposal. And for this, you kind of come up with some ideas. And in the moment when you want to do this kind of implementation, then you actually evaluate in NumPy those kind of questions, like how well will it work and so on, because you need to discretize and those kind of questions you need to ask. Okay, so let's discuss still a little bit about why the operator norm. So I only motivated this, that I can apply this to the Hamiltonian. And so let's talk about this. So let's say I have a unitary and I apply it to some state psi. I get some psi u state. I could have a different unitary and I apply it to state psi and I get some new state psi v. Okay. And in regular quantum mechanics, you kind of know how to evaluate the norm psi u minus psi v. Okay, let's do this. Which will be psi u with psi u. And then plus psi v, and then minus 2 times maybe real part of psi u psi v. Okay, so this is 1, this is 1. So I have 2 times 1 minus real part psi u psi v. So I can use the scalar product, the overlap of two wave functions, to evaluate how two different unitaries acting on the same state differ. Okay, which means that, for example, I could have a theoretical protocol, psi want this one, and this I can get by applying a unitary u to a state psi start. Okay, but I could have also like some bad idea how to implement this, and then I could be applying psi v and then psi get this in the lab. So you could ask how much do they differ, those wave functions, and then you would be looking at something like this. Okay, later I think I will be actually covering tomography and so on to extract this from experiments. So okay, so you get this number and you can evaluate it the standard way, but what we will get is that I will have psi u applied to psi minus v applied to psi. Okay, so what I'm getting is u minus v applied to some psi. Okay, so this is with equality. And now I can consider the maximum over all possible starting states and ask how the same starting point for those two different ideas for how to implement something distinguishes it. Okay, and that becomes our operator now, for example. Yeah, and so now if I look at this definition, it's maybe not so useful, but if you maximize this, then this becomes the maximum eigenvalue of u minus v, right? Because this is now the same thing. It's some unnormalized wave function maybe here. So you could call this norm phi. And this norm phi we were defining by, that's what I was doing here. Okay. So basically you start with a variation of energy. Okay. Then you look at this kind of scenario where you say, I apply two different ideas, something that I want, but something that I can get. And I ask, okay, how much am I missing my target? And you do this with the regular quantum mechanics, but then you say, okay, but what's the worst case? What's the worst starting state for this? And that will tell you the maximum eigenvalue of those two different unitaries here, of this difference. Okay. And this is one motivation. So, okay, I think this is bringing me almost to the end. Operator none. Quantify worst of unitaries. Quantify worst case performance of EU implementation versus the ideal. Okay, So if I want to run a quantum algorithm or a quantum control protocol for VIDL, how bad will it get if I apply it to an unknown state? So there will be a state which will be the worst state, you know, that will be the state satisfying some eigenequation. And basically that one will have the biggest error in that sense. So when we are talking about this operator norm on unitaries, we are talking about the worst case. Okay, that's one point of caution. But in principle, the quantum algorithms or protocols that we will be applying, they should work for any state. So in quantum technologies, this is actually a good measure of error. Okay, so why this is a good measure of error is this picture, where you don't know what will be the starting point, so you have to make sure that it works for all of them, at least with this guarantee. Sometimes it will be much better. Okay, and another thing is that this is the most stringent. So let's define an operator norm like this, max over psi, psi, a psi, psi, psi. But I could also define the two norm, which is trace a dagger a. And I could also define maybe the one norm. So trace of, I think I will need the square root. Okay, like this. Okay, and all of them are norms. So this is norm 1, this is norm 2, this is norm 3. And all of them can be in some way realized as limits of traces. Okay, so we are different norms. And what you have is, for example, that A infinity times, okay, this is always, let's say maybe there's always smaller than the two norm. So for example, if I would be applying this, it could have a different interpretation, but this would be a loose error bound, because there could be a physical setting, the setting that I just described, where this error is important. So basically, if you look at any other meaningful norms, they are actually useful. So probably next week I will tell more. If you will look at any different meaningful norm, if you already derived this bound on your state, okay, or on your preparation error bound, then you're good to go. Okay, so that's why this operator norm. So I will. So because of this, and because of this soundness property, in quantum control or algorithms, okay, let me write this. In quantum control or algorithms, we use operator norms. Okay, because operator norms are very nice for unitaries. I will give you one more example. Let me give you one more example. So if my operator A is the identity, then this norm labeled by infinity is just the largest eigenvalue, but this is already diagonal. All its eigenvalues are 1. Okay, if I look at the two norm, not two norm of 2, but two norm of this, okay, then this is trace of identity squared, which is identity, which is the dimension of my Hilbert space, which will be 2 to power L, the number of qubits in the system. Okay, L qubits. So just for the identity, it's already a humongous number. Okay, so basically there's a huge inflation. So this kind of stringent, the stringent property here is actually very useful. So there are two reasons why you will always use it. It naturally appears in this scenario of applying a protocol to a state. It can be quantum control, or it can be a quantum algorithm which uses gates which are implemented using quantum control. Those are maybe two aspects. Yeah, those are two applications where you care about this. And then that's why this is our error measure. Okay, so next week, operator norm of EIAT, EIBT to power n, and maybe delta t minus EI delta t times n a plus b. And we will show what is this function fn. And those are very nice bounds. One bound that you can do already today is sum from n equals n plus 1 until infinity, 1 over n factorial, a plus b to power n. Something like this, I think you can look at. So that's one idea how to get a bound, and this will be e to power a plus b. So it will be very, very bad. Okay, I think there will be maybe still somewhere 1 over n or something. So this is not my point, and I shouldn't be even saying this because it's kind of wrong. But one last thing that you can check, this is Poisson tail. Poissonian tail. And this is basically the giving you bounds on the cumulative function of the Poissonian distribution, very fundamental distribution. So it's good to know the series, very important in different applications. So if you do this, you will get a bad bound. Bad bound. And I will show how to get good bounds. When we will do this, I think this is a couple of sessions, we will understand Trotter-Suzuki decomposition. And once we have Trotter-Suzuki decomposition, I might digress to Picard-Lindelof and the Dyson series, because if I will have the Dyson series, I can give you a bound on, so maybe 1 to 2 months. If there will be interest in this, I will show how to get this trotterization T1 until IHTN minus the symbolic integral h of t. Okay, how to get some g of n function here. We can do this as well, which will give you quite a universal bound, but then probably it will be this kind of bound. Okay. So that's some things that we can do. And I think the idea is to maybe stop here and then discuss a little bit. Okay.